Hi, this is Hao-yang and Chia-Mu. Today we will give a review of the CVD method of the 2D materials. Next. 2D materials is a kind of materials that each atomic layer is linked by strong chemical bonds and adjacent layers are stacked by van der Waals force. Maxence is a 2D TMC-TMN materials which was successfully obtained by selectively etching a layer in max phase. Next. But chemical etching can only the materials is not stable. So recently, a CVD method enabled people to successfully grow 2D TMC and TMN crystal materials with various structures, as they have been shown on the slide next. However, researchers still facing some problems in using CVD method due to the limitation of the surface energy. The largest dimensions is about 100 micron. The layered structure will only grow if the surface energy of the material which was deposited is smaller than the growth substrate. Next. In this work, researchers choose copper and molybdenum bilayers as the substrate and anomia as the source of the nitrogen. The optical image, XRD pattern, and STEM image confirms only non-layered island, which micron scales was obtained without the adding of the silicon. The growth changed remarkably when element silicon was introduced. Figure 3 shows the furnace tube for the material growth. The silicon plate was placed above the substrate, and from figure 4, the silicon element was diffused onto the surface substrate. Next. From figure 5 shows the TOF-SMS map of the domain on the surface of the substrate. From the AFM image, the thickness is about 1.17 nanometer, which confirms the formation of the monolayers. Next. Figure 6 shows the optical image of the time evolution during the process. It shows that all the samples show the same optical contrast, indicating that they have a uniform thickness and the thickness remain unchanged. Next. From figure 7 and 8, the uniform contrast indicating that no additional layer were formed as time extended. The AFM image of the edge area indicating it's a normal layer structure. Next. Triangular domains with uniform thickness were formed initially and then expanded and merged until finally a centimeter scale uniform film was obtained. Next. From figure 13, a TM image can clearly show the grain boundary. Next. The thickness was independent of the growth temperature and the thickness of the copper foil in the broad growth window. After we introduce additional anomia gas thickness, next. After we introduce additional ammonia gas thickness domain formed on the surface of the monomer. Next. TEM, EDS, ELS, XPS measurement shows that the material contaminates anomalia silicon and nitrogen with a ratio of 1 to 2 to 4, and the crystal structure is hexagonal. Next. A honeycomb structure contrasted by alternating monomer and silicon atom was observed by STEM. Cross-section image shows that each single layer block consists of the layer of heavy atom sandwiched by 2 layers of light atoms. Atomic scale EDS mapping confirmed the sandwich scale, which have been shown in the slide. This structure was consistent with the previous XPS analysis. Next.
Density function theory is a computational modeling technique used to calculate electronic bank structure of MOSI2N4. In this article, two functionals were performed, which are PBE and HSE. It shows that MOSI2N4 has an indirect band gap of 1.744 and 2.297 eV based on the calculated PBE and HSE respectively. The optical properties were analyzed as well. The result shows that the absorption spectrum had 2 major peaks, one around 320 nanometers and one around 500 to 600 nanometers. By cross-referencing, they correspond to the excitonic transition, which was measured at 2.21 eV and 2.35 eV, which is shown in the figure. This is an acceptable range to agree with the PBE and HSE predicted values previously. Result shows that the MOSI2N4 has a high optical transmittance property due to its semiconductor nature. A monolayer of MOSI2N4 was transferred to a silicon substrate to analyze the electrical properties. The result shows that it has a typical p-type semiconductor behavior at room temperature in air and at 77 Kelvin in vacuum. It also had good ohmic contact with electrodes in both cases. Overall, mechanical property is one of the area of interest, and it was measured via AFM nanoindentation. To do it, a single crystal domain was transferred to a silicon substrate with a hole around 1,200 nanometers, which indicated by the yellow dotted line. As the force increases, the indentation depth increases constantly. This shows that it possesses elastic behavior, which derived from the linear elasticity curve. Also, a stability test was also performed. MOSI2M4 was put in different solutions for 24 hours, and the result shows that there is no significant defects or any change in structure. This shows that MOSI2M4 is sufficient to be placed in storing, processing, handling condition without any further protective layer required. Therefore, MOSI2M4 has a relatively good mechanical property compared with all other already known monolayer semiconductor. Lastly, substitution of different type of elements was tested through DFT calculations. We can thus replacing M with transition metals, the wide variety of M, A2, Z4 combinations provides manipulation of band gap. This is really important for electronics, optoelectronics, and spintronics applications, and which is shown in the figure, the band gap can be broadened or narrower. So in summary, in this research, researchers found that the introduction of silicon can passivate the dangling bonds, which make it possible to grow the 2D van der Waals layer at semiconductor scale. These materials in the form of MON2 layers sandwiched by two SiN layers. Also, density functional theory enabled to predict that MOSIN4 is semiconductor and has a better optical, electrical, and mechanical properties comparing with all other already known monolayer semiconductor materials. And that's all for our presentation, and thank you for your time. These are our references.